My name is Nico. I'm a systems programmer and I will be demonstrating the Statoscope tool to you today. Alright, as you can see, I just jumped into game as our latest hunt build. I want to do a live capture of basically hunt. So what I have to do is open the console again, type in eStatoscope enable. Let's first check that we have the log destination of Statoscope set to a socket. So we want to check that eStatoscope log destination is set to 1, which is socket. So when I have Statoscope open, which you can see here, it's a very basic interface that when I later go on connect, it will basically connect to my PC. So you can already see the port number here. If you do this with Xbox, for example, then as soon as you do eStatoscope enabled, it will show you the port that you should be connecting to. Whereas on PC, the port is fixed. So I have my log destination set to 1. So let's enable Statoscope. So what I want to do is eStatoscope enable and set this to 1. As you can see, my port number is 29527, which also matches my port here. Also, if you have your Xbox console, for example, make sure that your IP address is correct. And the port number also works. You can also say that you want to log directly to file while you're recording live as well, if you check this box. So let's connect, and you can see that immediately I'm getting swamped with a lot of results. These are all functions basically, which you can see under the functions profiler. So there are the various threads, the physics thread, main thread, audio thread, network thread, which all log their functions and the length of the functions. So if I look at this, for example, we have an audio internal update here, which takes a certain amount of time. We have the render thread to process certain commands, which takes a certain amount of time, and a lot more smaller functions. We can switch them all off. If you right-click on a parent here, then it will switch off all children. So what we are left with now is basically the overview, where you can see you have the frame length, the loss profiler time, memory, threading, graphics, and the overview about, again, frame length. So we can switch them off as well if we want. And what we can do now we're all left with the frame length, for example. So again, I can show you when we add data groups and remove data groups at runtime. Say I'm not interested in the frame length. So if I do eStatoscope and do data group and I do F minus, then what should happen, as you can see now, the F data group has been totally dropped. So basically the frame length is not recorded any longer. If I add it back with a plus, you can see it's all back up. So this is basically your live recording. Also, you have a screenshot option here. You can see here now there is no screenshot right now actually taken. So if you say, cool, like this is, for example, QA is running your build, then what you can do is tell them to also record screenshots. So for this, you have let's have a look at the Statoscope, actually. Statoscope. What we have here is the screenshot capture period. Currently it's set to -1. -1 obviously is off. So let's set this to, let's say, 1 second. Screen capture period, let's set this to 1 second. So what you should see now, if I go back into Statoscope and go in here, you can see it's actually taking screenshots. So if I was to move around now, for example, we can see later on, if we go back to the Statoscope, that here in this section, we have the screenshots. So you can kind of verify that, for example, QA has done something, they moved into certain sections, you can see where your performance loss is. So you can kind of locate where your performance problems are and then replicate them later onwards if you want to. Let's close the live connection and let's go into a deeper memory profile that one of our QAs has done. So I have 2 QA runs here as an example. So they were both done with the same build. One build had an optimization in it, and I would like to know if the overall performance or the frame millisecond time was better than the last one. So there's 2 options you can do here right now. Either you can drag your file basically into Statoscope, and it will open the file. Now, if I was to add the second file into Statoscope, it would open a new tab, which is probably not what we want exactly. What we want, if you do like middle mouse button, then you can close the tabs, of course. So what we want to do is we would like to have a direct comparison between the two. So if you drag both files, if you select them both, drag them both in at the same time, then you get an overlay. You can see this in your logs here. So now we have an overlay of 2 logs actually taken by QA. It's not always quite fair because, like for example in Hunt, QA will play the game differently, so it's not 100% comparison, but it gets you a quite a good overview if the average FPS has increased or not. So looking at the interface that we get, at the top we have the scale, so we can scale by frames or time. You can see it makes quite a difference, which is basically your axis here. To navigate in this panel here, you can do right click to zoom in and out, make it bigger and smaller. And if you do left click, you can basically drag the view. Also, you can switch on and off the different comparisons in this case by clicking these buttons here, switch them totally on or totally off. And like we already have seen, you can switch off certain regions in this tool here. Make sure when you re-enable a region, for example frame length, you see it will not be shown here because the parent has to be enabled as well. You can also change the range which you would like to profile, or look at the profile of your capture. Because, for example, you have QA, they go into the menu and then they start the game, and you don't know actually, you want to overlay, you just want to profile the time that they were in game and not when they were in the menu. So, I mean, we have screenshots here, for example, so you can kind of quickly see what has your QA guy been doing. Or you can go into the user markers, and if you go into the levels, you can see that there are markers set. So, for example, here, start symmetry is basically when I launch into the game. So you can see it's a blue guy who actually at this point launched into the game. So if you right click on this and use this as a start, you can see it automatically adapted your frame time here. So if I look at the screen for the blue guy, let's switch off the red one, for example, you can see actually this is right when you got into the game. I mean, like, you can still change this a bit, like to just as you like. I mean, for example, I don't want to really profile right now the section where the guy is actually loading the level. So let's say I'm going in by, as you can see here, this shows frame 1860, so I have to increase the frame count at the top by 1860. So you have a bit of math in your head, but let's say we're going to do 31,000 as the frame start. Let's double check with the screenshot. We're already in game. So do the same for the guy in the red. He's not really in game yet. So he's going to be in game about frame 15,000, 16,000, roughly, just to do a quick comparison. So he's already in game, and that's cut off the end as well for this guy. So this is at the end. So cut off about 20,000 frames. So this guy is also fully in game now. So we have both lines, basically all players are in game. And what we can do now, in this case, we can have the frame length, for example, which is calculated here, and you can see the average basically. So what you can see is that the first capture has a better average than the second capture. So we could probably say that the performance change that was made although it's the same build with a different performance patch, that it already helped. This guy was playing the same game on the same PC, but doing 2 different captures. What we can also see in this build is that you have these black lines, which are basically user markers. So let's concentrate on those right now. The user markers are basically, as you can see, you have the level start, you have layer switches, so you can see when are your layer switches happening. But you also have something called file access. So you can see here that there's something which is actually a bug in the game right now. We're actually compiling shaders during the game, which we don't want to do. So these will probably have frame dips. We can also see that these are actually DDSs here. So this would be the main thread actually loading textures. So this is probably the map background loaded. So something that happened in the game, which might probably have a UI impact. So the UI all of a sudden had to load some textures. But right here, for example, we can see that certain shaders are loaded, which should not be loaded. So this is something that our rendering guys are taking care of right now. So talking about the frame length, let's concentrate on the frame length here. We can see it's quite spiky, so it's quite hard to see what's going on. We can see we have a very big spike here for some reason, and the rest of the frame length is just very wavy. So if we want to even it out, there is this tick box at the bottom here, like the radius button. So we can have a moving average. So by moving average, you average the last 5 or 6 data values, and you average them out. So all of a sudden you get a much smoother curve. So you can see a bit more, rather than this edgy curve, you can see a bit more what's going on. Thing is, if you average things, then you will not find your spikes, because the spikes will be averaged into your results. So you might see a little peak, but it's not actually a huge peak that you can see. So if you select local max instead, it will keep the max in this case. So it will smooth out the curves, but the max values are very clearly shown. So you can kind of see in this case, every time we were loading data from disk, when we go back to the user markers here, so you have loading actually data, maybe for the UI, and you have loading data here for shaders, so actually shaders compiling in this case. You can see that every time this happened, there was actually a frame spike. So every time this happened, the user was not having a consistent frame rate. So you can now correlate the actual frame spikes to certain events in your game. In this case, we can see it's actually loading of shaders that actually caused the frame spike. In this case, I've loaded an example. In the example, we can see a section of the game actually running. So what I switched to is the function profile view. So we can see a lot of the functions. So we have function profile markers that you can set in game. And you have to be aware that there is a basic set of function profile markers enabled. And to enable all profile markers that we have, you have to do profile_deep. When you do so, however, that will also inflict a cost during profiling. So your game will run a bit slower because of the cost that the profile deep, actually the additional function calls that are recorded, will impact your game. What we can see though here is that these are all our functions that we wanted to profile. This is just the main thread, for example, as you can see. So it's calling to the different modules of the engine. For example, this calls into the system, it calls into the CRY renderer, and the network, the game itself. This would be your project if you have the profile markers in there. And we also have other threads. We have the audio thread, we have the network thread, we have the physics thread, we have the job systems merged, which is a bit special. So this is basically all the job system worker threads all merged together as one. So you can see what they're all calling as well. In this example, what you can see, I activated the main thread. So a quick thing again, just right click, disable all, right click again, enable all. Always make sure that all ticks are down to where you want to go. And we can see here, for example, there's a few spikes in this capture. So what's actually happening here? So we have, if I switch this off quickly again, I enabled the frame length time and put a bit of an averaging on it. And what we can see, if we enable this again, there's quite a few big chunks which are kind of are very visible. And we can also see, if I zoom in a bit, that it does affect the frame time. So what actually happened here was, if I go on it, it says sync main with render thread. So for me, this kind of shows that actually we're waiting on the main from the main thread on the render thread. So there's actually the main thread idling here in this case. So actually the bottleneck is not on the main thread, but it will be on the render thread. So what the render thread could be doing, it could be drawing, but it also could be waiting on the GPU to finish its workload. So basically we can drill into certain functions here if we really are interested in why our game is running slow, what's happening. I mean, you can zoom out a bit and see there's a few more functions at the top. Kind of just try your biggest functions. I mean, most of the functions are synchronizing, so having a sync function is not directly a bad thing, but you should find the correlating sync and who's actually triggering the sync. So in this case, the render thread, for example, would have been the slower one of the two. So I would like to know what happened there in order to remove that spike in the future. So if I look at the render thread, we can see there's the exact same spike that I could also see on the main thread. So we have it here, and then if I enable the render thread, we also have it here. So we can see here that the render thread has taken a very long time to present. So my guess here is basically that it's waiting on the GPU to finish its work. So it could be vsync, for example, or just GPU being busy. Another thing that you can do, I mean, you have all your functions showing that you can filter by a certain function name. We usually, like for example, you want to find out where you have to wait for data. Usually we name those functions with wait and something, the function name. So if I type in wait, hit enter, you can see that on all threads now it will select all the wait functions that are have been done. For example, render thread, there's a wait for GPU flag here. You have the network, there is a wait on network here. And these are all the functions. Doesn't mean it's a bad thing, doesn't mean it directly impacts your frame rate, because for example, if the streaming thread is actually, like in this case here, if the streaming thread is waiting, that means it's just not having to do any work. So there's no additional textures having to be loaded or things like this. Okay, so this summarizes this webinar about the Statoscope tool. I can only encourage you to check out the documentation on docs.cryengine.com and have fun playing around with it. Bye.
My name is Michael Madsen, and I will talk you through analyzing memory consumption with our MemReplay tool. On the screen you will notice a screenshot from our game Hunt. This is from a build from a few months ago. You might notice that the memory usage here is quite high. At this point in time, the game is using almost 18 gigabytes of memory, which is a bit more than you usually want your game to use. But the trouble is, how do you figure out why it's using 18 gigabytes of memory in the first place? Well, that's where our MemReplay tool comes in. As an example, I have prepared a slightly modified build of our current Hunt code, which contains an intentional memory leak. If you pay attention to the debug information, you can probably see that the memory consumption is steadily rising. Again, how do we figure out what is happening here? Well, in order to do that, we will first need to close down the game and tell it to create a memory log. So we will quit the game. So in order to create a memory log, we will need to start the game with a command line parameter. We type in the name of the executable and then we add -memreplay. You can follow this up by a extra argument to tell it how to save the file, what name to give it. There's also the option of transmitting the data directly to MemReplay, but I'm not going to go through that part through this tutorial. To keep things simple, we will simply start the game with this MemReplay switch. As you'll no doubt notice, the performance of the game while MemReplay is running has reduced drastically. This is unavoidable as it involves a lot of extra overhead because every single allocation and deallocation will be tracked. If you pay attention here to the top right of the window, you can see that our memory consumption is still growing, and we also have this line showing the size of the current log. I think at this point we've collected enough data to pinpoint the issue, so I will go ahead and stop the logging manually. You don't have to do this, quitting the game also works, but it can be nice to have a well-defined endpoint for your log. You simply do that by typing MemReplay stop into the console, and as you can see, the MemReplay line has disappeared from the display info, and we can now switch over to the actual MemReplay tool in order to diagnose this issue. So we will quit the game, and next we will start up the MemReplay tools, which you will find in the tools folder of your CRYENGINE installation. You may have an older version of CRYENGINE. In that case, I would suggest you still use the latest version of the tool from the latest version of the engine. We do our best to keep it backwards compatible, and generally you will find bug fixes and other things that make it easier to analyze these things. over in our game folder, we will find this setmrl file, which contains the log data for this analysis. We can simply drag this onto MemReplay, and it will start the analysis process. This can take a while, especially if you have a large log file, because again, there is simply a lot of data. You can get symbols from externals. You can get Microsoft symbols from the symbol server if you want to. Usually it's not necessary. The most important thing are the symbols for your own game, which you will be asked to provide usually. So we will do just that. It may ask for more symbols. In the latest release of MemReplay, it will try to automatically get as many symbols as it can. If you cancel a symbol request dialog, it will simply assume you have already provided all the symbols you need, which is generally the case because your game module will be very early in the log file, and once it's seen one of them, it will find the rest automatically. So we can simply cancel this at this point and let it continue to analyze. The symbols bar will jump up and down as it discovers more symbols that need to be resolved. This is normal behavior. Now that MemReplay has finished analyzing a log file, we are presented with these two graphs, which show us the amount of allocated memory over time. The top graph here will use the number of allocation events as the x-axis, whereas the lower graph will use the number of frames as the x-axis, which allows you, as I move the mouse over here, the black line is moving quite rapidly at the top, whereas the similar line at the bottom is moving in like steps. These two lines correspond to each other. So this particular line in the frame view corresponds to this particular line in the allocation view. From here, we can select an arbitrary range and view the allocations that took place during that time frame. We see this rising slope, so we're going to suspect that this is where our memory leak is located. We'll just grab a randomly selected amount of time, which should fit quite well with what we're looking for, and then we click the D view to view details for this selection. Here we can select the type of analysis we want to use. Generally, you want to keep this as delta. The allocation range here is selected from the range we selected over here. You generally don't need to modify it. All you really need to do here is click Go. And we can immediately see a hierarchical view of where all of our allocations have taken place. And we can now expand this, if we want, to get a bit deeper. So we see that here in the Create System interface, it and all of its children are responsible for an additional 76 megabytes of allocations. It's a pretty good chance that we will find our offending function further down here. So we keep expanding. Here it splits up because the doFrame function is associated with different lines representing children. Again, we're generally interested in the largest one, which is these 74.4 megabytes. So let's zoom down even further. And oh, look, we have a method here that claims to not be leaking any memory, except it very clearly is. And this is, of course, the method I added in order to highlight the error in question. As you can no doubt see, there is this method called definitely not leaking memory, which clearly is not doing its job because it has been leaking almost 75 megabytes of memory. We can see here in the file line address that this is located in the file system.cpp at line 1526, and indeed, if we switch over to Visual Studio, we can see that yes, there is indeed a memory leak here because we are simply allocating memory that never gets freed again. This is of course an intentional example. In actual projects, these things can be buried further, but you can dig in and figure out where these things go in the end. So I've loaded up a new memory lock in order to show you a slightly more complicated example, which with a bit more data, which makes it easier to discuss some of these functions of MemReplay. So this is a log file captured without the memory leak. This is again a game of Hunt. We have gone into a level twice and exit it back out. And let's say we would like to see what the difference is in memory consumption between the end of the first time we go into the level, which is going to be here, and the second time we exit the level, which is going to be here. So we can simply drag a range as before and ask for the delta computations. This is a slightly bigger range, so it takes a little longer to compute, but it is generally quite fast still. So we have here the delta view of these differences. We can see that a lot of these allocations are coming from the render thread. It is a very large block. We can simply click over here to jump straight to that area. There is approximately 2 gigabytes of extra allocations here, which is not necessarily a problem. We can dig in here and see where all of this memory is being allocated, but sometimes it's not really enough to see where it's allocated. We would also quite like to know what's been allocated. For this purpose, we can use the context tree feature. We can simply select whichever part of the log we're interested in, or whichever part of the delta view we're interested in, select it and click this C button to generate a context tree. This will go through all of these allocations and assign them into buckets based on markers that exist in the code. So as we can see, there are approximately 2 gigabytes worth of allocations still. We have 1500 megabytes of those associated with creating textures. We have some shadow maps, texture pools, and so on and so forth. And from here we can dig into whichever thing we think is using more memory than it should be. Perhaps we do not expect this voxel streaming engine to use as much data as it actually does. So maybe we want to see the details for just these particular allocations. Well, we can select anything here and click the details view again, and it will generate another detail view, but this time filtered to that specific category. So we can now dig into just this particular subsystem and see exactly where it has its own allocations. This can be very helpful when you're dealing with fixed budgets, like perhaps you assign your textures 2 gigabytes of memory. Well, then you don't really need to dig into those 2 gigabytes of memory if you're under budget there. Another thing we might want to do is hide certain parts of this view. Again, if your texture budget is 2 gigabytes, well, 1500 megabytes is fine, so we don't really need to worry about that. So we can use the exclude feature to generate a new tree map that excludes just that. This allows us to see more detail on the right-hand view and also make sure that we don't need to worry about other parts over in the tree view on the left. But by having this data excluded, we can more easily see the large problem spots that might be present but not really visible in the other view because the texture size is simply dominating. You will also notice that there are some allocations which are simply labeled as MISC. This is because there is no specific label for these. Again, though, you have the possibility to get the details about every single allocation that is considered a MISC allocation. And you will be able to see exactly where your memory is being allocated and deallocated. In this particular thing, we are dealing with render thread command processing. You will also notice that all of these allocations end with this C MemReplay record alloc or similarly named functions. This is an implementation detail of how we actually track these allocations. So in the game, there is a custom memory allocator which intercepts all calls to new, free, malloc, and so on. And this is then the function that does the actual recording. This is not something that the MemReplay tool knows about. It can't assume that this is what that is for, but in our case, we actually do know that that's what it is. We can, again, choose to exclude this node, but we probably still want to keep that data there. So what we can do instead is use the skip function to skip this entire file. We'll make the assumption that anything that is allocated inside MemReplay itself isn't actually MemReplay doing the allocation, but it is simply recording. So we can skip by file, and this will give us a new view where we can narrow things down a bit further. So the previous MemReplay record alloc is not going to be visible. All of the allocations that were associated with it instead show up under their function that called the functions inside the MemReplay tool. There's still some stuff we can exclude here or skip. In this case, we want to skip the renderer's tracking functions. So again, we will add that to the skip. We will add this to the skip. So after skipping enough data, we get this filtered view where we can see that it's directly create texture 2D. In this case, that is using 785 megabytes of memory. Maybe we want to zoom in on some of these other details, like this block. We can simply double click over here to zoom the view into that specific area. In this case, you'll notice that this is actually a negative allocation. This is because in the time frame we're examining, this module has freed more memory than it has allocated. Sometimes we're not really interested in what gets freed if it was allocated outside of our time frame. And there's actually a way we can deal with this. If we go back to our graph view, we can use the tools debugging no freeze analysis. This will again generate this details view that we've seen before, but this time it will ignore any freeze for allocations that happen outside of our range. This narrows down the view to only show the allocations that start within our given delta and are not freed within this delta. After the analysis is freed, we can now see we'll have slightly more allocations happening here that haven't been freed in this time frame. Now, this isn't necessarily a problem. In our case, I selected an arbitrary range of allocation events. This may or may not have been between frame boundaries, so the render thread might be very busy doing something, and this is why it has a lot of allocations right now. This is not necessarily a problem. However, suppose we suspect that there is a problem with the render thread. Suppose we suspect that there is too much memory allocation associated with it over time. Well, we can ask to plot the function by simply right-clicking it on our tree view and selecting plot. Again, we can select which level of detail we're going in through. In our case, we will select function here. Usually you want to select either function or file. Function is usually most relevant because it will give you everything associated with this exact function. You might also want to use file line to see everything that this exact line of the function is associated with, because sometimes you might want to plot different parts of the function. In our case, we will plot the entire function. And now that the plotting has finished, we see a red line in our graph which shows us the amount of memory consumption by this function over time. This is throughout the entire span of this log file. And so we can look at this and say maybe we don't think this is a reasonable amount of memory to use at this point in time. Well, we can then go in and see what makes it different in this particular time frame. And we can narrow down our analysis to get closer to the actual problem. There's also the possibility that we don't want to limit this particular function in any way, but we would like to subtract this from the view in question. We have the ability to add a plot to this graph, and we will simply go with an expression that asks to subtract plot 3. We will simply go with an expression to take the consumed graph, which we can get the data for by $1, and we will subtract the data for the render thread processing. So we can enter this as an expression, and we get a new line in very light blue, which shows us the amount of memory usage by everything except the render thread. And again, we can look for any unexpected spikes that might more easily show up when we have separated out the data like this. With that, this covers all of the most basic functionality of MemReplay. This is a very advanced tool, and it has very advanced features that can help track down even more isolated problems. But these are very case specific, and it will be an entire different session to go into details about those. This, however, should be sufficient to help you get started in tracking down those nasty memory leaks and figuring out how to deal with them.
And we are back. We did have one question come up during the broadcast from Joshua, who's asking about markers. I think this is with respect to Statoscope being added by the engine, or whether there's a way to add them at runtime if you want to target a specific moment that needs investigating.
Yeah, I mean, the way the Statoscope tool works, it's an intrusive profiler, so we set certain profiler markers in code, so they're fixed, but it is possible to add them over the console as well. So I mean, you can always, you already saw in the video that you can add them with a plus or minus certain groups, data groups. You can also set that you want to add a marker in the console, which you can then later use when you when you are actually looking at the Statoscope result.
I had just a general question. We had kind of been talking during the broadcast about the impact on performance of the profilers themselves. And the kind of long answer these guys gave me was that it really boils down to experience, kind of feeling it more than doing it by the numbers. Can you give any tips based on your long experience with this about how to account for that, or how much of a factor it really is? I think if I was developing, I'd kind of want to feel reassured, you know, how much to worry about that.
I mean, I kind of already kind of touched it slightly. I mean, the way we profile is that, you will have code running within the code. So as soon as you activate Statoscope, you are actually activating a lot more code that is executed per frame. So this will have some performance cost. So if you're profiling and your game is running exactly on the 30 FPS mark, then potentially you are actually, if you wouldn't be profiling, run faster than this. So usually you wouldn't run slower, that's for sure. It's in a way, it's a bit of experience. In the end of the day, you have to kind of judge of where you are losing time. You don't want to profile just this one function, which you think is a great function, and you really, really optimize the most out of it, but yet it's only called once per frame, and it's like a really small function not doing much. You want to really pull down on the extra cause of something that slows you down. So it could be something extreme as an IO stall. So basically you're loading a shader from disk, and you actually have to, say, wait on the main thread for the shader to completely have loaded from disk and then be compiled and loaded into the engine. Or it's something more that you, for example, you're doing updates on entities that are not even visible. So it's more another problem that you're actually doing work which you shouldn't do. This is the other approach of optimization. You should really try and not calculate things that you shouldn't calculate. Yeah. If you want to add something.
Yeah, so obviously what Nico said here is true. If you are in a situation where you're worried about the impact of profiling, you can, of course, turn some of it off. In the case of Statoscope, the fewer data groups you have, the less time the engine will need to spend writing out the data for that. So if you already have a decent idea of where you're interested in looking, then you can use that as a reference to sort of minimize the order of profiling. Also, for something like MemReplay, MemReplay has a lot of runtime overhead, but when you're doing MemReplay profiling, you're looking for memory usage. You're not really concerned about time. So that's a trade-off you make in that case.
What about the memory logs themselves? How much disk space should you have set aside? How big can the logs get?
They can get quite big. So how large they get depend on how long your profiling session is. So, for example, the more allocations and deallocations happen, the larger the log will get because every single one gets written out. The large log file that I showed in the presentation took up 2.7 gigabytes of space. In the past, I've worked with logs that were more than 4 gigabytes. We've occasionally run a log for a period of 24 hours. They also get quite big. But the good thing is that these logs are compressed, so they take up a lot less space than the raw data. Again, going with the log file I showed in the presentation, if you decompressed that, it would be approximately 53 gigabytes large. So you save a lot of space that way, and you can get a lot more data out of it. It does take a while to load these large log files, of course, but sometimes you need that amount of data, and then of course, yeah, you need to allocate the disk space.
Also, I mean, it always depends on the tool as well.
Yes.
Whereas MemReplay, it will need the whole information, because if you allocate something, it will need to know when you deallocated it. So if you allocate something, say at the start of the level, and you deallocate it at the end of the level, then you would have to profile this whole time in order to match these two allocations. Whereas with Statoscope, I mean, you could, for example, if you really wanted to, you could actually split up the logs. You stop your Statoscope run for a short second, and then you start it again, creating a new file. And later on, you can actually then offset it with the sliders to then give you as if it's one Statoscope run, basically. But usually, I mean, you're looking for Statoscope. I mean, I think when we do our Hunt QA tests, they end up between 150 or 300 megabytes, depending on what data groups you include. I mean, usually the 300 megabytes ones are mostly the ones that actually also include screenshots and things like this. So obviously, it really depends what you profile and how much data there is.
Is the bandwidth at which they're written worrisome enough that you'd want to route it to a solid-state drive, or a regular hard drive is going to be fine?
I mean, it's always like an I/O, so it's on a thread, so it doesn't stall the main thread or the render thread, so it will have some impact, of course, on taking away resources from the game running. But other than this, it should be as smooth as it can be. Writing to file. I mean, even if you stream it out and directly over network, you're only paying the network cost. For example, if you were to run on the console and you stream it to Statoscope, then yeah, you just pay the network cost. So on coming back to your question, then in that regard, if you were to profile on a console or if you have two platforms, basically you have two PCs, and one PC would have Statoscope running, and the other one would have the game running, and you would connect with that PC to your game. You would pay less cost, of course, because it's like one programming running less, which is taking away CPU resources, but it's not always required. I mean, this is like a really hardcore case where you really want to drill down on something that you think was changing the game so much that it's running on your PC because of the tool, like the Statoscope tool running in the background, that you really then want to go on a different PC, but that's usually not the case.
You mentioned consoles. Are these profiling tools, do they actually run on the console platforms? And if so, is there any differences we should be aware of?
Yeah, so for Statoscope, it should just work out of the box. You send the data usually to another PC, in that case, the PC development from. I think you can also have it save it to the disk. For MemReplay, that also works with the console. There are a few extra requirements. So for PlayStation logs, you will need the PlayStation SDK, because we need one of the tools to actually resolve memory addresses properly. And Xbox, you also need to make a mini dump while your game is still running, because this allows you to this extra information that we need to resolve the memory addresses to the correct lines of code.
Okay. We had another question pop up from Jesse. He asks, does the tool also work seamlessly with C# projects? That was not answered earlier, so I'm glad you asked.
So the way MemReplay works, it's on the C++ side. So it tracks all the allocations on the C++ side. So C# allocations that you do in C#, which don't boil down to eventually drilling to the C++ side, they will not be tracked.
Yeah.
That answers the question, I think.
Okay. Yeah. If that didn't answer your question, please ask a follow-up. Joshua, I think this is a new question. Are there any common areas where you see low performance in a game using CRYENGINE?
It always depends on the game, I guess, right? You have games where you say you have 100,000 entities. I mean, then the entity update might be really slow. You have games where you have tons of particles, then it's the particle area. I mean, in the end of the day, for the game, you want to find a balance of where you want to allocate your precious time of the frame, and where you can say, okay, maybe here in this case, I don't need 100,000, I only need 80,000 entities. Let's see how we can reduce this, even if they don't update, but maybe the user doesn't see, because there are, I mean, simplest case, say that they're 2 kilometers away, you don't see them. Maybe you don't need to update them.
Do you find that the tools reveal things you're surprised by in terms of what's killing the performance, or is it pretty much expected?
It depends. Like, well, usually like expected is bad, right? Because that means you did something wrong. I guess I mean a surprise, right?
In terms of areas of the engine, kind of what the question was referring to.
Yes.
So if you go back a while, we actually discovered a fairly severe memory leak in another profiling tool, as it happened, because Hunt does some things a little bit differently when starting things up, and this exposed a bug that actually caused one of our other profiling tool to leak several gigabytes of memory every time you change the level.
That's a surprise.
That was very much a surprise, and we're glad we fixed it.
I mean, yeah, the engine is developed by quite a few people, so we're not perfect either. So you usually find something that's like a scenario someone has not thought about can happen. I mean, you try to be as general as possible, but there are always cases where you call something in a different order than you would have thought. So there can be surprises. It's good though, because I mean, for example, for Hunt, it shows us that every now and then we started reloading a shader, which then caused a spike in the frame. I mean, it's very easy to see in the tool. It just like says here's an I/O axis, which you don't want to have really, except from your streaming thread. You want to have that on the main thread. But it just clearly showed there was an axis on the shader, and that means there's a spike. So that was something surprising because it shouldn't happen, and that bug got fixed as well, which obviously helps everyone out there playing Hunt, so getting it a bit more faster.
I'm just being mindful of time because I know Nico has a meeting that he can't miss at 4:00. Guillaume asks, is there anything particular to know about using these tools on a dedicated server?
They should just work. I'm a little unsure how it works if you're using a Linux server, which is still possible, but certainly on Windows should just work.
I mean, they should work. I mean, all they do is it's coming from the C++ side.
Yeah.
So it doesn't. I mean, there's not that much difference in regard. Yes, of course, Linux is different to Windows, but the API calls that you make within the engine should be the same.
Yeah. The main problem you might see on Linux is I do not remember off the top of my head if MemReplay can resolve the symbols.
Yes, the symbol resolution.
But for Statoscope, it should just work.
Okay. General question about Statoscope: what kind of data can you log through it?
I mean, I can refer you to the docs CRYENGINE webpage where it's called data groups. There is, you can go from like screenshots, so you can see how the person played the game. I mean, it was always helpful. It's one of the most helpful things usually, because if you are not the person doing the profiling, that means you can see what did the person see. And even if you later on have a look at how it worked, like how your result is, you might want to go back and think, yeah, this is where I saw the boss. That's why all of a sudden there was a bit more calculations that had to be done, or there was like 10 players all of a sudden on screen. So other than this, I mean, you can go into more detail on the engine. For example, you have all the worker threads. I mean, all the jobs, like the job system exposes all the information about all the jobs that it's running, so you can see how long they took, how much CPU usage you get per frame on these worker threads. But we also, I mean, not for the 5.5 release, but for the 5.6 release, we'll expose the GPU markers, which means you get a lot more insight on how the GPU is working, like how are the different, because it's a very fixed, like there's one step after the other on the GPU pipeline, and you really want to know, my game is slow, I'm waiting for the GPU, where is it hanging, like what took so long? Is it the shadow calculation? Is it like some other light calculation? Something like even like a post-processing pass? All these things that can take for some reason you don't know, that can take longer. I mean, for example, it could have been that your shadow calculation is very, very expensive because someone decided, I'll just add this lamp, or even, for example, in the case of Hunt, you can add like flash grenades or something like this. So if you add those and you say, okay, all of these actually create huge shadow volumes, then all of a sudden you throw 4 or 5 of them in one pile, and the engine will get slower because the shadow calculation will take longer. And this is like what the GPU markers will then show you kind of directly. It's like, look, this is the actual path where it took so long. Everything else on GPU went as usual, but this one took a bit longer.
Okay. I think we've got time for about one more question. And before I forget, if you have follow-up questions or questions that didn't get answered today, you can email us at education@CRYENGINE.com. It's probably the best way to get in touch. And also, if you want to express interest in other webinar topics, courseware, or anything kind of educational related, education@CRYENGINE.com. So Jesse has asked, can these tools be utilized in a live setting to log information from different machines to check performance and runtime for PC?
I mean, if you mean by live setting, the game is out in the live, it's live and played by people, then I would say no, because they are usually there just for development. So you can, surely, if you have QA, you can connect to your QA person on that PC, but it's not there for live settings. No. So for this, you can usually, what you can do is you can build something that traces this information and push it onto some server, like where you can actually access the logs, but they're not built for actually being out there in the live environment, because they also have performance costs. They also carry a lot of code with them, which you don't want into your released game. I mean, there's another point, is that usually these tools are disabled when you build your release game, because you want to be your release game as lean as possible. I mean, it doesn't have to do calculations that it shouldn't do, because just because you want you want to profile, like the guy playing your game doesn't mind. He just wants to play it as fast as possible. But if you do want to test it in your release build just before you bring it out, I mean, you shouldn't ship with it. There's option CMake. I think it's called option release profiling. So this will allow to enable some lightweight profilers. Not all of them, but it has some, which should help you figure out what's going on in your in your release build. Because sometimes release and profile can be different because of the profiling tools being on and off. There's a lot less code being executed in release builds. There's more optimizations done by the linker and the compiler. So it's rare that we actually profile release builds, because profile usually gives you a very good drift of where your normal slow zones, like where you are actually losing performance. It usually shows you the best.
Yeah. All right. That is all the time we have today. I hope this was helpful and answered some questions, and wherever you're at in your game development process is going to be useful information to you. Again, if you'd like to comment, ask follow-up questions, or make requests for future topics, email us at education@CRYENGINE.com or find us online. And thank you so much for joining us today, and we will see you next time.
Thank you.
Ciao. Bye.